Good morning. This is Math 0310. This is March the 6th. Welcome, everybody. A couple of announcements. WebAssign homework. There's WebAssign homework due today. You have two sections due today. One that covers 9.1, 9.2, and 9.3 in your textbook, and the other one covers 9.4. That's due at the end of the day today. That's an extension from Sunday. Then you have three sections due on the 18th, which is after spring break, 9.5, 9.6, and 9.7. And then the week after that, you have 9.8 and the section on complex numbers due. So try not to get behind on the WebAssign homework. Remember, I do drop 4 of those at the end of the semester, but you want to try to keep up with it. That should be a good grade by the end of the semester. Remember, you have basically an unlimited number of times that you can attempt problems on WebAssign. So you miss something, you can always go back and redo it and bring your grade up until the due date. So don't forget that. Also, don't forget that I have some extra videos that go with each section of what we've got in WebAssign. You can always go and click on those, and it gives you still another explanation for what we've been covering. The Exam 2 review is posted. I posted it actually probably about 30 or 40 minutes ago, and so you can go and look at the Exam 2 review. It's a very lengthy review. Lots of problems on it, which is good for you because it means it's lots of practice problems. All of the solutions to those problems are on the review also. So try to take advantage of that review, especially as we get into spring break coming up next week. The Exam 2 window, remember, is March the 22nd through the 27th. And don't forget that I will be on campus on March the 21st and March the 22nd. I'll talk more about that. I'm talking more about that on Thursday of this week, and then when we come back after spring break, but I'll be on campus the 21st and the 22nd. Spring break is next week, so don't forget, no lectures posted next week at all. So we'll take 2 days off, Tuesday and Thursday of next week, no lectures posted. I will be available to meet with you in the WebEx office during spring break, some at least. So if you want to come by and set up an appointment with me, I have no problem with you doing that. Just send me an email, and we'll try to come up with a agreeable time that we can meet in the WebEx room and go over some things. Please take advantage of that. I don't have a problem with you trying to get with me over spring break to get some extra help on some things. And then let's see, finally, today we go off-road a little bit. When I say off-road, we're not using the textbook that we've been using all semester. We're taking a section out of another textbook from Open Stax. That's the intermediate algebra textbook. It is an Open Stax textbook also. I have taken that section out of that book and uploaded that section only onto your Google site for the course. And so don't forget that you have access to this section just by going to the Google site and going to syllabi and other documents. And it's sitting in there. And so, take advantage of that to get access to extra problems and to get access to explanations about some things like that. We are in the process of finishing up finishing up radicals and exponents. So we've done all this stuff on radicals and exponents, and what we're kind of doing now, one of the main things, there's two main things really that I would say is that radicals and exponents are kind of geared towards. One is, especially with square roots, we're trying to prepare for solving quadratic equations. That's where we're headed next, is to look at methods for solving quadratic equations where factoring won't work to solve the quadratic. And so square roots come into play all the time in those other methods. In fact, in all of the other methods, square roots come into play in various places. And so that's one reason why we've been talking about simplifying square roots. The other reason is, and especially with exponents, the reason we've been talking about it is to prepare you for college algebra, and in particular things like solving other kinds of weird equations that you do in college algebra, and then also looking at logarithms and exponential functions and talking and using the stuff with exponents to build in towards talking about logarithms. So, all right, so that's where we are. That's what we're coming out of now. So please practice those kinds of things frequently over the next week or two as we're getting into spring break, because radicals will be a big deal on exam 2. So today what we are doing is we are covering complex numbers. Now, so what we need to do is talk about what the heck we mean when we talk about a complex number, and then talk about how to simplify complex numbers, and then add, subtract, multiply, and divide. And then complex numbers will come up again as you deal with quadratic equations, and again in college algebra when you're dealing with polynomial functions. Like my college algebra students right now deal with complex numbers relatively often because we're in the middle of talking about polynomial functions. That's a big place where it comes up. All right. So the way to look at this is, think about back when you were a kid, or think about, for some of you that are with me today live, and maybe some of you who are watching the recorded version later, think about your own kids and where they are with dealing with numbers. And as you go through this process of dealing with numbers when you're a child, and you start gradually getting older, the first thing you learn how to do is you first learn how to count. Whoops. Sorry. So you've got the counting numbers. Now, the counting numbers, another term for the counting numbers is the natural numbers. Now, those are the first numbers that you first learn how to use as a kid. And when you use those counting numbers, you're not really even counting how many of something. You're just learning numbers in a row. So you learn how to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You learn how to count your fingers, but even when you learn how to count your fingers, you're really only naming your fingers. That's finger number 1, that's finger number 2, that's finger number 3, and so on. So you learn this kind of rote memorization of the counting numbers or the natural numbers, right? And it's just these numbers, 1, 2, 3, 4, 5, and so on. Right? And you gradually push the envelope. You learn how to go further and further into that list and everything. And then somewhere along the line, and it's different for different kids start to figure out that those numbers actually mean something, that those numbers mean how many. Right? And one way that you can tell whether a kid is at that stage of how many is to take 5 pieces of candy, or pennies, or whatever, buttons, something like that. Put five of those things in front of you. Here you are right here. And here is the child right here. And you put 5 of the same thing across like that, and you ask how many, or who has more. And basically they would typically say, well, we have the same. But then if you line yours or theirs up like this and yours up like this, now notice you still have the same number. But now they say, well, I have more. Well, they still aren't to the point where they're talking about how many yet, right? Because to them, spreading them out like that means they have more, even though they really don't have more, right? So you could experiment with your kids at home about where they are with this, and you're talking about kids who are 3, 4, 5 years old, depending on the kid, as far as how they develop with this kind of thing. Everybody figures it out. Some of them just figure it out earlier than others. But eventually kids start talking about how many. And then once they get to that point of how many, somewhere along the line, they confront a situation where the counting numbers don't do them any good anymore. Because, for example, they have 3 marbles in their hand. Their big brother comes over and steals those 3 marbles. And now how many marbles do they have left? Well, they don't have any marbles left at all. But notice the counting numbers don't do any good anymore. And so what you do is you make the transition from the natural numbers or the counting numbers to what we call the whole numbers. Now, a kid doesn't formally do this. The kid doesn't formally say, hey, I am going to make the transition to the whole numbers. But that's what they do. And the whole numbers are simply the counting numbers with the number 0 thrown in. Right? And the whole numbers now are that set, 0, 1, 2, 3, 4, 5, and so on. Right? So what happened? The natural numbers are the first set of numbers that a child learns how to use. The natural numbers somewhere along the line don't satisfy all their needs as far as describing things around them. And so what do? They come up with this new number, 0. And they use the number 0 together with the counting numbers. And then the whole numbers emerge. And the whole numbers do just fine for a while for a kid. Until all of a sudden, somewhere along the line, a couple of situations come up. A couple of different situations come up. First of all, they might be talking about money and talking about the difference between $1 and 75 cents, right? Or $1 and 6 quarters, things like that. And so the decimal numbers start coming into play, and fractions start coming into play. They give a pizza, and somebody says, let's divide this pizza up into 8 slices. We're dividing that pizza up into eighths, right? And so somewhere along the line, decimals and fractions come into play, and so a kid needs the decimals and fractions. And also, somewhere comes into play with money again, where you have $10 in your checking account, and then you write a check or you use your debit card or whatever for $15, and you overextend your checking account. And so with money in particular, what all of a sudden happens? Money and pizza and things like that. You need decimals and fractions. Right? And then you also, so that's one thing. And then you also need negative numbers. Right? Because like when you're overextending your account, you've got negative numbers are needed. So a kid makes the transition from the whole numbers to the integers. You start using negative numbers, right? And so the negative numbers is this set of numbers, right? It's the whole numbers and all their opposites. Those are the integers. And again, it's the same process, isn't it? You're going from the natural numbers to the whole numbers to the integers. And then finally, you include these, well, not finally, but then next you include the decimals and the fractions, and you go on to the rational numbers. The rational numbers are numbers that can be written as fractions. Right? Numbers that can be written as fractions. And that includes the decimals where you're talking about money and things like that. So again, this process of going from the natural numbers to the whole numbers to the integers to the rational numbers, it's simply a natural process that a human takes as they go through their lives, where they hit a new situation where the set of numbers that they were using isn't satisfactory anymore, right? The whole numbers are not satisfactory when you're trying to divide up a pizza. The whole numbers are not satisfactory when you're trying to deal with money, especially when you're talking about dollars and cents. And so you've got to go on to things like the integers and the rational numbers, because you have situations where the whole numbers just don't do you any good anymore. And then, so you've got these numbers that can be written as fractions are the rational numbers. And then you, in school, in high school or middle school, somewhere along the line, you start dealing with numbers that can't be written as fractions. And those numbers are what we call the irrational numbers. The irrational numbers are numbers that cannot be written as fractions, that can't be written as fractions. Now, for a long time, it's very smart people way back, In Pythagoras' time, in the Greeks' time, the Egyptians' time, there was people who believed that there was no such thing as numbers that could not be written as fractions. And so they didn't believe that those kinds of numbers existed. In fact, people were put to death if they, in some cases, or marked in some way if they believed that there were numbers that couldn't be written as fractions. So all sorts of crazy reasons why people would want to kill some other people. And believe it or not, these were sometimes situations where people were put to death for believing things like this. But part of it was because these numbers were associated with these people's religion also, and so people were very passionate about it, and very passionate about what kind of numbers they believed in or didn't believe in, which is crazy, right? But the irrational numbers are numbers that I'm going to flip the screen here. The irrational numbers, again, these are numbers that cannot be written as fractions. And so those would be the numbers would be like pi would be an example of a number that can't be written as a fraction. Pi is approximately 3.14, but pi, actually, its decimal doesn't terminate and doesn't repeat. Square root of 2, the square roots, square root of 5, things like that. 1 plus the square root of 5 over 3. Those kinds of numbers that we've been talking about over the last week or two, those are all examples of irrational numbers. The decimals for those don't terminate and they don't repeat. They can't be written as fractions. Now, I know 1 plus the square root of 5 over 3 is a fraction, but when I say a fraction, I'm talking about where you've got a whole number divided by a whole number. There's no way you can take any of these numbers and write it as a whole number divided by a whole number. It's not possible to do. So when you take the irrational numbers and the rational numbers, and you stick those two sets together. Now, the rational numbers are the numbers that, remember that I said that could be written as fractions. So that'd be like 2/3 and -5 halves and 8 and 0 and 3.75, things like that. Those are all numbers that can be written as fractions. And you take the rationals and the irrationals and you throw them together, and you get what we call the real number system. And that is the number system that we have been talking about and using in intermediate algebra so far is the real number system. All the numbers we've been talking about are either rational numbers or they're irrational numbers. You can't be both, because remember, rationals are numbers that can be written as fractions. Irrationals are numbers that can't be written as fractions. So they don't have anything in common. But when you throw them together, you get the real number system. And that just serves just fine for almost all purposes, kind of in everyday life. But believe it or not, there are applications where even the real number system, in fact, there ends up being a lot of applications where the real number system is not satisfactory. And that's where we are right now in this class, right? We've been going through this process, and you've been going through this process in your life. And your kids are somewhere in this process also, where they go from one set of numbers to another, and as they confront a situation where the set of numbers they've been using doesn't work for them anymore, then what do? They kind of sort of like make up new numbers, right? So to go from the natural numbers to the whole numbers, they threw in the number 0. To go from the whole numbers to the integers, they threw in all the negatives. To go from the integers to the rational numbers, you throw in all the fractions that are not whole numbers, right, that don't divide out. And then the irrationals, you throw those in. Those are numbers that can't even be written as fractions. There's actually more irrational numbers than there are rational numbers, believe it or not. All right, so the real number system is where we are now. This is what we've been talking about up to this point. But now, in algebra, we would really like an equation like this to have a solution. X squared equals -1. Now, when we know that when you square a real number, you always get a positive, right? If you take a real number, no matter what it is, and you square it, you always get a positive answer. So notice the equation x squared equals -1. What I want to be able to do is I want to be able to take a number and square it and get a negative answer. we've actually also discussed this in a different way earlier, within the last few days, because we've talked about the fact that something like the square root of -4, what have I been telling you to write in that case? I've been telling you to write not real in a problem like that, right? And it's kind of the same thing as x squared equals -1. When you square a real number, you always get a positive. So there is no real number you can square to get -4. Well, we want to change that, and we want to extend the real number system one more time. And so that's what we do. And essentially what we do here to make that extension, to make this jump, is we define a new number. And we define this number to be I, and I has the property that it is equal to the square root of -1. That's its property. That's its definition. All right. So it's a crazy number. It's the number that has the property that when you square it, you get -1 as an answer. Now, I is sometimes called, and this is not necessarily a great name, but this is what it's called, it's called an imaginary number. Now, an imaginary number is the name suggests it doesn't really exist, but that's just kind of an unfortunate historical name that was associated with it, and that we're kind of stuck with today. So we continue to call this the imaginary number, and numbers that have i's in them, we call them imaginary numbers, but they exist just as much as anything else does. What is the number 3? The number 3, if I write that symbol down, one thing it describes how many marks I'm making right here, right? The number 3 describes how many marks I've got right there. So that's a definition for the number 3, right? The number 3 is not an object that you can touch or anything like that. It's a symbol that describes a certain property, right? It has things associated with it when we write that symbol down. Well, the number I is the same thing. In some ways, it's just that its definition's a little bit different. We define it to be the square root of -1. That's its definition. Just like the number 3 describes how many marks I have right there. But this definition kind of opens up a whole new game for us here, because then it allows us to talk about something like the square root of -9 or the square root of -4, things like that. Because I can write the square root of -9 as the square root of 9 times the square root of -1, and the square root of 9 is equal to 3, and the square root of -1 is equal to I, right? Whenever you see the square root of -1, you can replace it with I. And so even though the square root of -9 is not a real number, we can write it as an imaginary number. We can write it as 3i. The square root of -4, in exactly the same way, would be the square root of 4 times the square root of -1. And the square root of 4 would be 2, and the square root of -1 would be I. So we write the square root of -4 as an imaginary number as 2i. It's not a real number, but it's definitely an imaginary number. And notice that what happens here is if you square it, remember the square root of a number is supposed to be equal to something that when you square it, you get the original number back. And look what happens when I square 3i, for example. When I square 3i, I get 9i squared. But then don't forget what I squared is equal to, right? That I squared and -1 mean the same thing. And so whenever I see an I squared, I can replace it with -1. So this is 9 times -1, or -9. So notice 3i is a number that has the property that when you square it, you get -9. 2i is the same thing. When I square 2i, I get 4i squared. But there's my I squared again, and I squared is replaceable by -1. And so this is 4 times -1, or -4. Right? So 2i is a number that has the property that when you square it, you get -4 as the answer. So it's appropriate to write these as the square roots of these numbers. The square root of negative 49, then, based on what we've been talking about, this would be the square root of 49 times the square root of negative 1, or 7i, right? The square root of negative 1, again, you always replace it with I. The square root of negative 100 would be the square root of 100 times the square root of negative 1, or 10i. Now be really careful. This applies to square roots. This doesn't really have anything to do with cube roots, right? So the cube root of negative 8, this is not imaginary. Remember, the cube root of a negative number is just a real number. It's negative 2. So, so what do you have here? The square root of a negative number the square root of a negative number is imaginary. The cube root of a negative number is a real number, right? So, so the square root of negative 64 is 8i, right? The square root of a negative number is imaginary. The cube root of negative 64 is just negative 4. It's a real number, right? So don't get square roots and cube roots confused here. That's common to do, so that's why I wanted to talk about that. Okay, and let's see if we have the square root of negative 50. Right, 50 is not a perfect square, so we simplify this kind of like we've been doing with radicals in the past. We break it up into 2 factors, and in this case it would be negative 25 and 2. And so then what's the square root of negative 25? Like we've been talking about over the last 5 minutes, this would be imaginary. This would be 5i. And then this would be times the square root of 2. Now, a little word here about how you write this out. So I have 5i times the square root of 2. Don't ever write this as 5 square root of 2i. WebAssign, unfortunately, might do that sometimes, but I don't want you to get in the habit of doing that because it's tricky as to whether the I is underneath the radical or not, right? You don't intend it to be under the radical, but it might look like that right here. And so don't write it that way because you want to be clear about what's under the radical and what's not under the radical. All right, the square root of negative 40 then, we would break that up as the square root of negative 4 times the square root of 10. And then the square root of negative 4 would be 2i. It would be imaginary, so you have 2i times the square root of 10. Now remember, I is not equal to negative 1. I is equal to, and I'm going to repeat this frequently, I is the square root of negative 1. I squared is negative 1. Right? Those are kind of, in some ways, the 2 definitions for the imaginary number. You'll see it written actually both ways like that. All right, so hopefully this is maybe beginning to make a little bit of sense here. So if you have a problem like this one, let's say we have the square root of negative 72 plus the square root of negative 8. Do not try to write these or add these together. Remember, these are not like radicals, so you still have all those properties that we've talked about with square roots. And so remember, with square roots, you can only add together square roots that are like radicals. So these are not like radicals, cannot add these. But what you can do is simplify both of them. So you simplify both of them by writing the square root of negative 72 as the square root of negative 32 times the square root of 2. And square root of negative 8 you could write as the square root of negative 4 times the square root of 2. So the square root of negative 36, that would be imaginary. So that would be 6i times the square root of 2. And the square root of negative 4, also imaginary, it would be 2i times the square root of 2. And so now these are like radicals, right? They're both square roots of 2. And so we can add these. And so this would be 6i plus 2i, just like any like terms. You just add those together, you get 8i times the square root of 2. All right, so I wanted to kind of point that out. The next thing I want to point out here before we start tackling complex numbers specifically is we have talked frequently about the fact that, let's say square root of 3 plus the square root of 5, not like radicals, cannot add these together. So not like radicals cannot add. But then the square root of 3 times the square root of 5, if it's multiplication, it is okay to multiply these, and you do get the square root of 15. And so we stated this, and we've actually used this property often, but if you go back and look at the lecture, when we first stated this property that two square roots can be multiplied together, I did mention very briefly, and you might have completely missed it. You might have completely missed it if you were either attending live or watching the recorded version, is there is one exception to this rule. There's one time when you are not allowed to multiply two square roots together. A and B can't both be negative. A and B cannot both be negative. So you cannot multiply them together if they're both negative. So let me give you an example of what I'm talking about. The square root of negative 4 times the square root of negative 9. Right? If they're both negative, you're not allowed to multiply these together. So instead what you do, so you cannot, this is not equal to the square root of 36. You cannot add them together. Or, I'm sorry, multiply. But you can simplify them. So the square root of negative 4, that's imaginary, right? Because it's the square root of a negative number, so that would be 2i. The square root of negative 9, the square root of a negative number, it's imaginary also, and you get 3i. Now you can multiply these, and you get 6i squared. And then don't forget what 6i squared is equal to. I squared is always replaceable by negative 1, so that's 6 times negative 1. And so notice you get negative 6. See, if you had multiplied them together, you would have gotten the square root of 36, and that would have given you positive 6, right? That's not true. And so the answer here is negative 6. So the moral to the story here is that if you have two square roots that you're multiplying together that are both negative, don't multiply them together. Instead, simplify each one of those first. So the square root of negative 9 would be 3i. It would be imaginary. Square root of negative 25 would be 5i. It would be imaginary. Multiply those together, you get 15i squared. I squared is negative 1, so that's negative 15, because this is 15 times negative 1. That's negative 15. All right, so that's the one exception to the rule. It's not a big deal. To be honest with you, you're not going to encounter that very often at all. As a college algebra student, in fact, I can't really think of a place as a college algebra student you would deal with that. All right. So now the complex number system. Complex numbers are any number that can be written as a plus bi. A number that can be written in that form, a plus bi, is called a complex number. And you'd be surprised to find that the complex numbers, it's a different set than you might think ordinarily. So these are examples of complex numbers. So 3 plus 5i is an example of a complex number. All right, a is 3 and b is 5. This is sometimes called, by the way, the real part, and the 5 is sometimes called the imaginary part of the complex number. You don't necessarily have to know that, but that's true. You have the real part and the imaginary part. So negative 6 plus 1/2 I is a complex number. Right? Negative 6 is the real part, 1/2 is the imaginary part. The square root of 3 plus the square root of 5 times I, that would be a complex number. Right? So A and B can be any real numbers that you want. They can be positive, they can be negative, they can be square roots, all that's okay. Even a number like this, even a number like 8I is a complex number. It's just that the real part is 0. So this is really 0 plus 8I. And believe it or not, a number like negative 6 or 5 or 0, those are complex numbers also, believe it or not, because negative 6 would just be negative 6 plus 0I. So notice the complex numbers include all the real numbers we've already talked about, and then all the numbers with the i's in them also. So the complex numbers are a set that includes everything we've been talking about, but it also includes all these numbers that have i's in them as well. Now, what we want to spend the rest of class today talking about is we want to talk the rest of the day about operations with complex numbers. So when I say operations with complex numbers, I want to talk about adding, subtracting, multiplying, dividing complex numbers. All right, so addition is by far and away the easiest of the operations with complex numbers. So as a simple example, if you have 8 plus 3I plus negative 10 plus 11I. Right, that would be a typical example of an addition problem with complex numbers. It's super simple to do. All you're doing here is simply adding the real parts, the 8 and the negative 10, which would be negative 2, and adding the imaginary parts. 3I and 11I would be 14I. Like I said, very simple to do addition, because it's just a matter of collecting like terms is all you're really doing. So adding complex numbers, I'm hoping, should not be a big deal for you at all. Subtraction is not a whole lot more complicated. If you have negative 5 plus 10I minus 8 plus 6I, right, that would be a typical subtraction problem. And the only thing you got to worry about here is the signs. So this is negative 5 plus 10I, and you distribute this minus sign through, and you get minus 8 minus 6I, like that. And then you collect like terms just like you do with addition. So negative 5 minus 8 is negative 13, and 10I minus 6I would be 4I. Right, and you've added them together, or you subtracted them rather. And so the subtraction is pretty much like addition. You just have to remember to change the signs is all you've got to remember to do. So that shouldn't be too big a deal. Multiplication, a little bit more involved, but it is still not bad. The only thing you have to remember with multiplication for numbers in the form a plus bi is always remember that I squared is equal to negative 1, because that comes up a lot in a multiplication problem. And so just keep that in mind. So let's say we have negative 6 times 3. Now, it won't come up in the first problem, but it'll come up afterwards. So the first example, we have negative 6 times 3 minus 5I. That's just the distributive property. This shouldn't be any different than even if you didn't know what the I was, this is probably what you would have done to multiply this out. So you get negative 18 plus 30I. And you're finished. So not a big deal. Now this next problem, you do have to be careful here, because now I squared equals negative 1 is going to come into play. It's still a distributive property problem. You're going to multiply through by 2I. And so 2i times 6 would be 12i. And then 2i times 7i would be, and this is where you have to be careful, this would be 14i squared, because it's going to be an I times an I. And then keep in mind the definition that I squared and -1, remember, are the same thing. So this becomes 12i minus 14 times -1. And so notice again, what I did here is I took the I squared and I replaced it with -1. Anytime you see an I squared, you automatically replace it with -1. So this would be 12i minus 14, minus -14, right? And so this is 12i plus 14. Now, usually when you're talking about operations with imaginary numbers, you try to write the answer in a+bi form. So 12i plus 14 is correct. I would not penalize you for writing that, but I also want you to look cool in the math lab when you're talking in the math lab. And so people might not think you're cool if you wrote it this way, if you wrote it 12i plus 14. You should write it as 14 plus 12i. You want to put the I terms as the second term, because you want to write a complex number in that form, a+bi. Like I said, it is not wrong to write the first way. I wouldn't penalize you for it, but you ought to write it the other direction. Okay. So, doing good. Now the next one, let's say we have, we're still talking about multiplication now. So multiplication just has more situations. Let's say we have 3 plus 2i times 8 minus 5i. Right, 3 plus 2i times 8 minus 5i. So this would be the FOIL method that you would use to multiply. Still the distributive property, remember, but this would be a FOIL method problem, because it kind of looks like two binomial expressions. So you just walk through the FOIL method. And so you get 3 times 8 is 24. Outside 2 would be 3 times minus 5i would be -15i. And then 2i times 8 would be 16i. And then 2i times -5. Now be careful on that last one, because this is where the I squared comes into play. This would be -10i squared. And then don't forget that I squared is equal to -1. So that comes into play in this problem. So you'd have 24. The middle two terms are like terms. So -15i plus 16i. -15 plus 16 would be 1. So you have plus 1i. And again, WebAssign will count 1i wrong probably, but there's nothing wrong with writing 1i. But they'll write it as just I instead of 1i. And then -10i squared, that's where the -1 comes into play, right? I squared is equal to -1. Right? So every place you see an I squared, don't forget you're going to replace it with -1. So this would be 24 plus I plus 10, or 34 plus I. Now this is not hard. You just have to remember I squared is equal to -1, and you should be okay here. The FOIL method is one reason by the way, flipping the screen back for a second, believe it or not, addition and subtraction are among the most missed problems on this exam, believe it or not. And the reason why is students, I'll give you an addition problem with complex numbers, and people will use the FOIL method there. Right, they'll fail to recognize that this is just addition, and that you're just collecting like terms here. So, don't forget that the FOIL method's only used when you're talking about a multiplication problem. Right, that the FOIL method is kind of a shortcut for multiplication. All right, so I think we're okay here. Let's do another example of the FOIL method to finish that out. So you have -6 minus 2i times -3 minus 5i. Lots of negatives in this one. So once again, FOIL. So you have negative 6 times negative 3 would be positive 18. Negative 6 times negative 5i would be positive 30i. Negative 2i times negative 3 would be plus 6i. And then here's the I squared coming into play in this last one. Right? Negative 2i times negative 5i would be positive, because it's a negative times a negative. And this would be 10i squared. And then we write down that I squared is negative 1. Not a bad idea for you to write down that I squared is equal to negative 1 on your test somewhere so that you remember that. So this one's going to be 18 plus, these are like terms in the middle, so that's 36i. And then 10i squared. So I squared is equal to negative 1. So wherever I see an I squared, I replace it with negative 1. So you get 18 plus 36i minus 10. And some of you might just go straight from 10i squared to negative 10. That would be okay. And so then this gives you 8 plus 36i. Right? 18 minus 10 is 8. And then just bring down the 36i. All right, don't forget the multiplication patterns that we have talked about back when we were talking about radicals. So don't forget that when you multiply conjugates together, don't forget that when you multiply any conjugates, a plus b times a minus b, right, that just gives you a squared minus b squared, right, that's the pattern for multiplying conjugates. So that pattern extends if you've got conjugates that are imaginary. So 8 minus 3i times 8 plus 3i. By the way, since these are complex numbers that are conjugates, these are sometimes referred to as complex conjugates. So when you multiply these together, it's the same pattern. You could just write down a square minus a square. So this would be 8 squared and 3i squared. And so 8 squared would be 64. 3i squared would be 9i squared, right? 3 squared is 9i squared. And then I squared is negative 1. So we have 64 minus 9 times negative 1, or 64 plus 9, finally 73. So notice when you multiply complex conjugates together, you end up with a number that is not imaginary at the end, right? All the i's would drop out in a case like that. All right, the other multiplication patterns we talked about, don't forget, we talked about squaring addition problems and squaring subtraction problems, right? That a plus b squared, remember, we've talked a lot about these patterns back with square roots. Same with a minus b squared. Right, so a different kind of pattern than multiplying conjugates, but still a pattern that we can use. So if you have 6 plus 5i quantity squared like that, if it's imaginary, it's still the same pattern. So that's what I would do, is I would just use this pattern to my advantage to multiply things like that out. Right? These terms would be 6's, and these terms would be 5i's. All that's going to be different here is that you're going to end up using I squared equals negative 1 at the end of the problem. So you have 36 plus 60i, and then this last term would be 25i squared. And then we use that I squared is negative 1 in this step right here. So you get 36 plus 60i plus 25 times negative 1. So that'd be 36 plus 60i minus 25, or 11 plus 60i. Right. Not, again, the only difference really in this multiplication from what we've done in the past is that you're using this definition that I squared is negative 1 is inside the problem there. All right, and so what we want to do now is we want to finish with division. And so division is probably the most involved of the operations. Is there a question?
Oh, sorry.
No, you're good.
No question.
You're sure?
It's because Abby was moving some keys in the keyboard.
Ah, okay, okay. All right, so division. So with division, the idea is this, that if you have an imaginary number in the denominator, if you're dividing by a complex number in the form a plus bi, then the strategy here is to multiply the top and the bottom. Remember, that's allowed. That's definitely allowed by the equivalent fractions property, that you can multiply numerator and denominator by the same thing and get an equivalent fraction. So we multiply the numerator and the denominator by the conjugate of the denominator, a minus bi. So if you do that, then you can rewrite this, and your hope is at the end you can write something in this form. And I'll just put capital A here and capital B, but that you can write something in the form a plus bi at the end. Right? So you're trying to eliminate any imaginary numbers in the denominator is essentially what you're trying to do here. So let's see how this would work. Let's say we've just got, let's start with something relatively simple. Let's say we have 6 over 3 plus I. 6 over 3 plus I. So see, you're dividing by a complex number. So the strategy is to multiply the numerator and the denominator by the conjugate of the denominator. So that would be the conjugate of the denominator here would be 3 minus I. You're trying to write this so that there's no imaginary numbers in the denominator. So in the denominator, you've got conjugates, so you know that that's a square minus a square. And it would be 3 squared and I squared. Like that. In the numerator, when you have a single factor like that, like a constant like 6, then just don't multiply it out. Just leave it as 6 times 3 minus I, because it's possible you could simplify the fraction at the end. All right, and so you get, and in fact, you're going to be able to in this problem. So you have 6 times 3 minus I, and in the denominator, you get 9 minus I squared. So I squared, you know, is negative 1. So you have 9 minus negative 1 there. And so notice you get 10 in the denominator. And see, you can see why I left the 6 sitting out in front there, because now I can divide out a 2 here, and the fraction actually simplifies. And you have a 3 and a 5 like that. So this would be 3 times 3 minus I over 5. Now, if you left the answer like that, I would probably not penalize you for writing it that way, but WebAssign probably will, because WebAssign is going to want you to write the answer in a plus bi form at the end, and this is really not an a plus bi form. So what you should do is multiply this out at the end. You have 9 minus 3i over 5. And then don't even write it that way. Split the fractions up so that you have 9/5 minus 3/5 I. That number is in the form a plus bi, like that. We have a constant plus or minus a constant times I, like that. Now, once again, what I be okay with that answer? Yeah, I probably would be okay with it. But you ought to be aware of in a textbook, they're likely to write it out as 9/5 minus 3/5 I. That's not uncommon there. All right, the next problem, let's look at this one. You have 3 minus 2i over 6, and let's say 6 minus I. All right, so you're dividing by this imaginary number, this complex number here, and so I would multiply numerator and denominator by the conjugate of the denominator. So you're multiplying numerator and denominator by 6 plus I right here, because the original denominator was 6 minus I. So you're multiplying by 6 plus I. Remember, you have to do the same thing to both the numerator and the denominator. So in the denominator, I get a square minus a square because I'm multiplying conjugates together. You could use the FOIL method if you wanted to, but remember, this is just a shortcut for that FOIL method. And so you have 6 squared minus I squared. In the numerator, you really have no choice here but to use the FOIL method to multiply this out. You're really going to have to do that. So using the FOIL method, you get 18. The outside 2 would be 3i. The inside 2 would be negative 12i. And then the last 2 would be negative 2i squared. Because you have an I times an I in that last one, that last term. All right, so that's all the multiplication there. And so now you've got to go through and simplify everything. So in the denominator, this would be 36 minus, and there's my I squared, so that's negative 1. So if you want to finish, the denominator is 37. In the numerator, you have an 18, and then 3i minus 12i is negative 9i. And then the negative 2i squared is going to be negative 2 times negative 1, or positive 2. So the positive 2 and the 18 give you a 20. So this is 20 minus 9i over 37. WebAssign probably will want you to write this in a plus bi form. So they'll want you to write this as 20 37ths minus 9 37ths I, like that. That's an answer that's in a plus bi form. And again, on an exam, if you wrote that answer, I would be thrilled with that. I'm not going to make a big deal about it. It's certainly not going to be too big a deal in college algebra of how you write it. But you should be aware of how you're going to write it in a plus bi form if that were to come up. All right, so we're kind of down to one example here, and then we will have finished what we need to do with complex numbers, so that'll be good. You have negative 3 plus 5i divided by 2i. So that 2i is technically 0 plus 2i. So if you're going to multiply by the conjugate of the denominator in this problem, the conjugate of the denominator is just negative 2i. Technically, it'd be 0 minus 2i, right? The original denominator, that's really 0 plus 2i. And so what we're really multiplying by is 0 minus 2i. But 0 minus 2i is just the same thing as negative 2i. All right, so let's see how this all works out here. In the denominator, all you have is 2i times negative 2i, so that's just negative 4i squared. I squared is equal to negative 1, remember. I've only said that a few times, right, in the last 30 minutes. So this is positive 4 in the denominator, because it's negative 4 times negative 1. In the numerator, you do have to use the FOIL method to multiply this out. So you have negative 2i times negative 3 is 6i. And then negative 2i times 5i is negative 10i squared. So I squared, once again, is -1. And so this is 6i plus 10 right there, because it's -10 times -1. All right, let's kind of clean up how we write this. So we really want to put the 10 first and the 6i second. So this is 10 plus 6i over 4, like that. And then this simplifies just like you would see a radical. And we saw this with radicals back in the last few sections, that if you had 10 plus 6 like times the square root of 2 over 4, remember we talked about that if there's a common factor in all 3 parts of a number like that, then you could divide it out. It had to be in all 3 parts. So then this would give you 5 plus 3 square root of 2 over 2. This is exactly the same thing with imaginary numbers and complex numbers. So there's a common 2 in all 3 parts. So you can divide that out. And so that leaves you with 5 plus 3i over 2. And then that would, and WebAssign, they'd write it as 5 halves plus 3 halves I. And again, I don't care which of these 2 ways you wrote it at all. Both of those would be fine. All right, so this is a quick rundown on complex numbers. We've gone through all the operations. We've simplified square roots. That's what I would ask you on the exam. On an exam, I'd ask you to simplify square roots. I'd ask you to add, subtract, multiply, and divide complex numbers. There are definitely a group of problems on your review on complex numbers. The textbook practice on this would be out of the section that I gave you. This is section 8.8 from the intermediate book. And remember, you have a copy of that sitting in your Google site in syllabi and other documents. And in section 8.8, I would want you to look at, on page 844, problems 409 through 467. Any of those odds would work just fine. Those would be good practice. So. All right, does anybody who's listening live here, you guys have been very quiet. You haven't asked a lot of questions recently. Does anybody have anything that they need to ask me or that they had a question about as I was going through this?
No, not at the moment.
All right, then go home and practice or stay at home and practice. Please let me know if you have questions about anything. Remember, I have online office hours today from 11 to 12 this morning, and then again 8:30 to 9:30 tonight, and then again tomorrow from 11 to 12, and on Thursday from 11 to 12. So don't hesitate to stop by my WebEx office for help. Otherwise, have a wonderful day, and I will hopefully see you on Thursday in live lecture.
Okay, thanks. Thank you.
Everybody take care.